Two people walk past each other on a pavement this afternoon, one heading north, one south, both moving at about 1.5 meters a second, the speed you walk down a corridor without thinking about it. Neither of them looks up. Neither of them will remember the moment. At the instant they draw level, one of them believes that a certain event in the Andromeda Galaxy is happening now. The other believes it happened 4 days ago. 4 days of the history of 1 trillion stars produced by walking. And neither of them is wrong, and there is no third person anywhere in the universe who could settle it. The usual story is that relativity means time slows down when you travel, and that this is the loophole that finally makes the stars reachable. Nothing slows down, nothing has ever slowed down, for anybody, in any experiment ever performed. By the end of tonight you will know exactly how time traps you in interstellar space, and it is not the thing you are expecting. Get comfortable. If you're the kind of person who enjoys finding out that something you were sure of was never quite true, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this, right now is not a phrase you will be able to use about anywhere else. Now, let's slowly settle in. On the 18th of November 2026 at 16 minutes and 7 seconds past 2 in the morning, Pacific Time, a small nuclear-powered machine built in the 1970s, will pass a line that nobody drew. There is nothing there. No boundary, no marker, no change in the darkness on either side. But at that exact second, Voyager 1 will be 16,094,799,096 miles from the Earth, and that number happens to be the distance light travels in one day. It will be the first object our species has ever made that a question cannot reach and return from inside 24 hours. Take a moment with that, because it is smaller than it sounds and larger than it sounds at the same time. If you sent a command to Voyager 1 on a Monday morning, the signal would leave the antenna at the speed of light, cross a gap of roughly 25.5 billion kilometers, arrive at the spacecraft on Tuesday morning, and the acknowledgement would come back on Wednesday morning. 2 days for one exchange. A conversation of 10 sentences with the most distant thing we have ever built would take the better part of a month. And here is the part that reframes everything. Voyager 1 has been flying continuously since the 5th of September, 1977. That is 49 years and 2 months of unbroken flight, without stopping, without slowing, at 17 kilometers per second, about 61,000 kilometers per hour, which is roughly 50 times faster than a rifle bullet and considerably faster than anything else our species has ever pointed away from the sun and released. 49 years of that, and the distance it has covered, measured in the unit that actually matters out there, is 0.0026 light years. Not 2.6, not 0.26, 0.0026. The nearest star to the sun is 4.2465 light years away. Voyager 1, after half a century of the fastest sustained departure in human history, has completed about 1/4% of the trip to the next star. If you scaled the journey to the length of a marathon, Voyager would be about 100 meters past the starting line, and it would have taken 49 years to get there. This is the honest starting position, and I want to be honest about it, because everything that follows tonight depends on you understanding how small our actual reach is before we start talking about what happens when it stops being small. Now, you have almost certainly heard the standard consolation for all this. It goes like this. Yes, the distances are enormous. Yes, the speeds we can manage are pathetic. But there is a loophole. Einstein found it in 1905, and it says that if you travel fast enough, time itself runs slower for you. The trip that takes 4 years for everyone back home takes less than 4 years for you. Go fast enough, and the journey compresses. The universe at very high speed gets closer. That is the promise. That is the thing everyone reaches for when the distances get depressing, and it is real physics. I want to be clear about that from the beginning, because tonight is not going to be a debunking. Every word of it has been measured. It works exactly as advertised. So let us ask what it has actually done for us so far. Voyager 1, moving at 17 kilometers per second for 49 years, has experienced time dilation. Its onboard clock has genuinely fallen behind the clocks on Earth. The effect is real, it is calculable, and the number is this: about 2.5 seconds. 2.5 seconds. That is the entire relativistic achievement of the human species, accumulated across half a century, aboard the fastest thing we have ever launched. Less time than the pause between two sentences, less time than it takes to put down a cup. The fastest human beings who have ever lived, the crew of Apollo 10, at nearly 40,000 kilometers per hour on their way back from the moon, spent a few days at a speed that gains them a few hundredths of a millisecond. The International Space Station, which has hosted people continuously for a quarter of a century, moves at 7.66 kilometers per second, and it displaces its occupants into the future of everyone below at a rate of about 1/100th of a second per year. Sergei Krikalev, who has logged more cumulative time in orbit than any other person alive, 803 days, is, as a result, roughly 20 milliseconds into the future of the rest of us. Permanently. He will never get those 20 milliseconds back, and neither will we. There is a scale model that helps, and I want to give it to you now because we will come back to it. Shrink the sun down to the size of a basketball and set it on the ground in front of you. On that scale, the Earth is a grain of sand about 30 meters away. The next star, the nearest one, the one Voyager will never reach, is another basketball, and it is 6,900 kilometers from where you are standing. That is roughly the distance from London to Delhi. And on that same model, Voyager 1, after 49 years of continuous flight, is about 18 kilometers from the first ball. It has left the neighborhood. It has not left the city. It is also, slowly, going quiet. As of April of this year, only two of Voyager 1's science instruments are still switched on, the magnetometer and the plasma wave subsystem. The cosmic ray detector was powered down in February of last year, the low-energy charged particle instrument this April. The plutonium is cooling. The power budget shrinks by a few watts every year, and the engineers turn off one more thing to keep the rest alive. There is something appropriate about that, given where tonight is going. The furthest thing we have ever sent is not being cut off by distance, it is simply being turned down, one channel at a time, until only the signal remains. So the picture at the start of tonight is a strange one. The loophole exists. The loophole has been verified to more decimal places than almost anything else in science, and the loophole has so far moved the entire human species about a 50th of a second out of step with itself. It is very hard to be frightened by a 50th of a second. Which is exactly the problem, because the thing I want to show you tonight is not a warning about how dangerous time dilation is. Time dilation, at the speeds we can reach, is a curiosity. It is a rounding error in a spacecraft's navigation software. It is the reason your phone knows where you are and not much else. The thing I want to show you tonight is what happens on the other side of that curiosity, and specifically, what happens if we ever solve the engineering problem. Because there is a widespread assumption, so common that it almost never gets stated out loud, that the difficulty of interstellar travel is a distance problem, and that time dilation is the answer to it. Faster ship, shorter trip, problem solved. By the end of tonight, you're going to know exactly how time traps you in interstellar space, and I can tell you now that it is not the thing you are expecting. It is not that time slows down. Nothing slows down. Nothing has ever slowed down in any experiment for anybody. What happens is stranger, and quieter, and much harder to escape. And to see it at all, we first have to take away the one word everybody thinks they understand. We have to talk about what a clock is actually doing. I want to retire a sentence. The sentence is "time slows down," and it is the most repeated and most misleading phrase in all of popular physics. It has done more damage to people's understanding of relativity than any equation ever could, because it points your attention at exactly the wrong thing. It makes you look for something that malfunctions, and nothing malfunctions. Not once, not anywhere, not for anybody. Picture yourself aboard a ship travelling at 99.9% of the speed of light. Your heart is beating at whatever rate your heart beats. Your coffee cools at the normal rate. If you set an atomic clock on the table, it ticks at exactly 1 second per second, because that is what a second is. You feel no drag, no thickening of the air, no sensation of a world running in treacle. There is no experiment you can perform inside that sealed cabin, none, not a single one at any level of precision, that will tell you how fast you're moving. And that last point is not a limitation of your instruments. It is the whole of relativity stated in one line. There is no such thing as how fast you're moving. There is only how fast you're moving relative to something else, and the something else always has an equal claim to being the one at rest. Galileo worked this out in 1632 with a ship and a jar of flies. Below decks, on a smooth sea, Nothing about the flies or the water or the dripping bottle tells you whether the ship is moving. Einstein's contribution, nearly 3 centuries later, was to take that seriously enough that it broke our idea of time itself. So if nothing slows down, what is the clock doing? Here is the answer, and it is the single most useful idea in this entire video. A clock is not measuring the flow of some universal river. A clock is measuring the length of the path it has taken. Physicists call the quantity proper time, and it is the only reading any clock has ever given, anywhere, ever. Think about 2 cars. They both start in the same town and they both end in the same town. One takes the motorway, one takes a meandering route through the hills. At the end, they park side by side and compare odometers, and the numbers are different. Nobody is surprised by this. Nobody says the second car's odometer was running slow. It travelled further, that is all. Clocks are odometers. They are odometers for a road that runs through 4 dimensions instead of 2, and the 4 dimensions include time, and the disagreement between 2 clocks that start together and meet again is not a fault. It is a measurement of 2 different lengths of road. Now, here is the part that should bother you, and I want it to bother you, because it is the mechanism underneath everything else tonight. In ordinary space, the straight line between 2 points is the shortest path. Everybody knows this. It is the first thing anyone learns about geometry, and it is true. In space-time, the straight line is the longest. I will say that again, because it does not go in the first time. The path through space-time that accumulates the most time, the most seconds on your own clock, the most experienced life between one event and another, is the path with no acceleration at all. The path where you do nothing. Every turn, every burn, every deviation, every clever maneuver makes that path shorter. Not longer, shorter. This is not a paradox, and it is not a trick of wording. It falls out of the geometry of space-time the way the Pythagorean theorem falls out of the geometry of a flat sheet of paper, except that space-time's version of Pythagoras has a minus sign in it, one single minus sign in front of the space term, and that minus sign is why adding distance to your journey subtracts time from your clock. Nature wrote a subtraction where our intuition expected an addition, and every strange thing you will hear tonight comes out of that one symbol. It is worth naming the one thing everybody does agree on, because relativity is not the theory that everything is subjective. That is the popular misreading, and it is backwards. Observers disagree about elapsed time. They disagree about measured length. They disagree about which events happened at the same moment. But every single one of them, without exception, computes the same value for the space-time interval between 2 events. The time term squared minus the space term squared. That quantity is the same for everybody in the universe. Relativity is not a theory about what falls apart. It is a theory about what survives when the obvious things do. There is a way of holding this in your head that I find more useful than the equations, so let me give it to you. Everything in the universe is moving through space-time at exactly the speed of light. All the time. Right now. You, sitting there, apparently motionless. You're moving through space-time at 300,000 kilometers per second, and you always have been, and you always will be. What changes is not the speed. What changes is the direction. When you're sitting still, all of that motion is pointed along the time axis. You're travelling through time at the full rate, and through space not at all. That is what sitting still is. When you start to move, when you walk across a room, or board an aircraft, or fire an engine, you rotate a little of that motion out of the time direction and into a space direction. You do not gain speed, you reallocate it. Every meter per second you gain through space is taken out of your progress through time, and the exchange rate between the two is set by the speed of light. Which leads to the extreme case, and it is worth sitting with. A photon puts all of its motion into space. It has nothing left over for time. Light experiences exactly 0 proper time. The photons arriving on your retina right now from a star 4 light years away did not spend 4 years crossing the gap from their own point of view. From their own point of view, insofar as that phrase means anything at all, they were emitted and absorbed in the same instant. There is no duration in between. The entire history of a photon from the birth of the universe to now, 13.8 billion years of travel, has a length of exactly 0. Light does not experience the journey. That is the price of going at the maximum rate, and the universe charges it without exception. There is a second consequence of the odometer picture that we will need much later tonight, so let me plant it now. If a clock is reading its own path, then the question, What time is it really has no answer. Not a hard answer. No answer. The word really in that sentence is asking for a universal coordinate, a master reading that all the individual odometers are approximations of, and relativity's position is that no such coordinate exists. There is no master clock. There is no committee. There is no view from nowhere. There are only world lines, each carrying its own honest total, and none of them privileged. That sounds abstract. It is going to become extremely concrete in about 40 minutes, and there is a third consequence, which is the one that connects the small end of this to the large end. If clocks measure path length, then a clock's rate depends on where it sits in a gravitational field as well as how fast it is moving, because gravity, in Einstein's later description, is curvature in the same geometry the odometer is measuring. This is why the ceiling of the room you're in is aging faster than the floor, not metaphorically, measurably. Your head is running ahead of your feet right now, by an amount we will put a number on shortly, and the number is real, and somebody has weighed it. So we have replaced one idea with another. Time is not a river. Time is a distance you travelled, and your clock is the odometer, and the odometer is always honest. Now, at this point you would be entirely justified in thinking that this is a lovely piece of philosophy, and asking whether any of it has ever actually been measured. Because it is one thing to say the geometry works this way. It is quite another to catch a clock in the act. It has been caught, repeatedly, with rainwater, with airline luggage, with satellites, with a staircase, and with a pair of identical twins. The best evidence for time dilation is not an instrument reading. It is a body count. Every second of every day, cosmic rays, mostly protons flung out of dying stars in the neighbourhoods of black holes, arriving from every direction, slam into the top of Earth's atmosphere at roughly 15 kilometres up. The collisions shatter atomic nuclei and produce showers of debris, and among that debris is a particle called the muon. A muon is essentially a heavy electron, about 207 times the mass, and it is unstable. Left alone, at rest, a muon survives for an average of 2.197 microseconds before it falls apart. 2.197 microseconds is not very long. Even if a muon travelled at the full speed of light, which it cannot, but let us be generous, it would cover about 660 metres in that time, and it needs to cross 15,000 metres to reach the ground. So essentially none of them should arrive. The arithmetic is not close. The muons should decay somewhere high in the stratosphere, and the surface of the Earth should be entirely free of them. Hold your hand out flat. Right now, several muons are passing through it every second. They are passing through the roof, through you, through the floor, through the bedrock underneath. About 10,000 of them strike every square metre of the Earth's surface every minute, and they have been doing it for the entire history of the planet, and by every reasonable calculation they should not be here. In 1962, two physicists decided to count them properly. David Frisch of the Massachusetts Institute of Technology and James Smith of the University of Illinois took a detector to the summit of Mount Washington in New Hampshire, 1,917 metres up, and they counted an average of 563 muons per hour arriving at that altitude. They published the result the following year in the American Journal of Physics. Then they took the same detector down to Cambridge, Massachusetts, 6 metres above sea level, and counted again. Without time dilation, the number at sea level should have been small. The muons had an extra 6.4 microseconds of flight time to survive, which is nearly 3 of their average lifetimes. The prediction from ordinary physics was that only a small fraction of the 563 would make it. They counted 408. 408 out of 563. Nearly 3/4 of them survived a journey that should have killed almost all of them. Work backwards from the survival rate, and you get a time dilation factor of 8.8, plus or minus 0.8, meaning that from our point of view, the muons' internal clocks were running at about 1/9 of the normal rate, which is exactly what their measured speed predicts. And I want to underline what kind of evidence that is. Frisch and Smith did not read a dial. They did not calibrate anything against a theory. They counted particles arriving, and the particles that arrived were physically there, and the only reason they were physically there is that their own clocks had run on their own path length rather than on ours. The American Physical Society has designated Mount Washington Observatory a historic physics site for it. The proof of the strangest idea in 20th century physics falls on you, silently, all day, every day. 8 years later, 2 men put 4 atomic clocks on commercial airline seats. In October of 1971, Joseph Haffel and Richard Keating bought tickets, actual tickets, on scheduled flights, for themselves and for 4 cesium beam clocks, and flew around the world twice, once heading east, once heading west. Then they brought the clocks home and compared them to the reference ensemble at the United States Naval Observatory. The prediction was subtle, and the subtlety is what makes the result beautiful. Because the Earth rotates, flying east adds your aircraft's speed to the rotation, and flying west subtracts from it. So the 2 trips should give opposite answers. The prediction was that the eastward clocks would lose about 40 nanoseconds, and the westward clocks would gain about 275. The measurement: the eastward clocks lost 59 nanoseconds, plus or minus 10. The westward clocks gained 273, plus or minus 7. The whole experiment cost roughly $8,000, most of it airfare. It remains one of the best value experiments in the history of science, and it did something specific and important. It settled the twin paradox with objects you could hold in your hand. 2 clocks, 1 journey, physically disagreeing on return, in the direction the theory said and by the amount the theory said. Then there is the version that runs continuously, that you personally depend on, and that would fail today if any of this were wrong. The Global Positioning System is a constellation of satellites carrying atomic clocks, orbiting at about 3.9 kilometers per second, roughly 20,200 kilometers above the ground. 2 effects act on those clocks in opposite directions. Their speed makes them lose about 7 microseconds a day. Their altitude, where the Earth's gravity is weaker, makes them gain about 45. The net result is a gain of about 38 microseconds every single day. 38 microseconds sounds like nothing. Light travels about 11.5 kilometers in 38 microseconds. That is the size of the error the system would accumulate daily if nobody corrected for it. And it would keep growing. Your navigation would drift by a city block within an hour, and by a small country within a month. They do correct for it, and the way they do it is my favourite detail in this whole subject. The oscillators are physically detuned in the factory before launch. They are set to run slightly slow on the ground, at 10.22999999543 MHz, instead of a clean 10.23, so that once they are in orbit and relativity speeds them up, they tick correctly. Somebody, decades ago, sat down and built time dilation into a production line. The precision has kept climbing since. In September of 2010, a team at the National Institute of Standards and Technology, Chin-Wen Cho, David Hume, Till Rosenband and David Wineland, published a result using 2 aluminium-ion optical clocks linked by 75 meters of optical fiber. They resolved time dilation across a height difference of 33 centimeters, 1 step on a staircase. They also measured it at relative speeds under 10 meters per second, which is slower than a bicycle. The Institute's own summary of what they had proved is the finest sentence any press office has ever produced. Your head is older than your feet, and they put a number on it. Over a 79-year lifetime, standing 33 centimeters higher, costs you about 90 billionths of a second. In February of 2022, a group at Gila pushed the same measurement down to a height difference of 1 millimeter. And finally, the version with people in it. Scott Kelly spent 340 consecutive days aboard the International Space Station between March of 2015 and March of 2016, while his identical twin brother Mark stayed on the ground. The station moves at about 7.66 kilometers per second, 17,500 miles an hour, which is fast enough that the speed effect beats the opposing gravity effect of being 400 kilometers up. Scott came home approximately 5 milliseconds younger than his twin, 5 milliseconds, after a year in orbit. There are older receipts too if you want them. Herbert Ives and G.R. Stilwell measured the transverse Doppler shift in hydrogen canal rays in 1938, which was the first direct laboratory sighting of the effect and predates everything else on this list. In 1959, Robert Pound and Glenn Rebka measured the gravitational version over the 22.5-meter height of a tower at Harvard, using an effect in iron nuclei so precise it could resolve a frequency shift of 2.5 parts in 1,000 million. In 1976, Gravity Probe A carried a hydrogen maser 10,000 kilometers up and came back agreeing with Einstein to 70 parts per million. And in 1977, a storage ring at CERN whipped muons around a circle at a Lorentz factor of 29.33 and watched their lifetimes stretch by exactly that factor, under accelerations exceeding 1 million times Earth gravity. which incidentally settled a question nobody had been able to test before, namely whether acceleration itself damages a clock. It does not. A clock only ever cares about its speed at each instant, and Sergei Krikalev, the cosmonaut I mentioned earlier, is the record holder for the whole species, 803 days in orbit spread across 6 flights, which places him about 20 milliseconds into everyone else's future. He is the furthest into the future any human being has ever travelled, and the distance is roughly the length of a blink. So here is where we stand. The effect is real. It has been measured with falling particles, with flying luggage, with orbiting satellites, with laboratory staircases, and with 2 brothers who share the same genome. It is engineered around every second by a system that billions of people rely on to find their way home, and the total amount of time travel any human being has ever performed is about a 50th of a second. That gap between an effect verified to 15 decimal places and an effect that has never mattered to anyone is not an accident. It is the shape of the curve, and the shape of that curve is the next thing we need to look at, because it is the reason all of this has been so easy to ignore, and the reason it will stop being easy the moment anybody succeeds. The reason time dilation has never mattered to anybody, and the reason it will matter enormously to the first people it ever does matter to, is the shape of one curve. The number that governs everything is called the Lorentz factor. Physicists write it as the Greek letter gamma, and its definition is 1 divided by the square root of 1 minus your speed squared over light speed squared. You do not need to hold the algebra. You only need to know what gamma is for. It is the number of seconds that pass at home for every 1 second that passes aboard your ship. At rest, gamma is exactly 1. 1 second here, 1 second there. Perfect agreement. That is the world you have lived in your entire life. Now let us climb the ladder, slowly, 1 rung at a time, because the shape of the climb is the point. Start at 1,000th of the speed of light. That is 300 kilometers per second, nearly 20 times faster than Voyager 1, considerably faster than anything humanity has ever sent anywhere. At that speed, gamma is 1.0000005. A full year aboard your ship cost you 15.8 seconds against the people at home. 15 seconds in a year, at 20 times the fastest thing we have ever built. Move up to 1% of light speed, 3,000 kilometers per second. This is the low end of what serious interstellar design studies talk about. The fusion concepts, the nuclear pulse drives, the things that exist on paper and in wind tunnel models and nowhere else. Gamma is 1.00005. A year aboard costs about 26 minutes. 26 minutes. That is your reward for a technology that does not exist, running for a full year. 10% of light speed, 30,000 kilometers per second. This is Project Daedalus territory, the 1970s British Interplanetary Society design, a 54,000-ton fusion ship, and the number that gets quoted whenever anyone wants to be optimistic about fusion propulsion. Gamma is 1.005. A year aboard costs 1.8 days. Now apply that to a real trip. At 10% of light speed, the journey to Proxima Centauri takes 42.46 years measured from Earth and 42.25 years measured aboard the ship. You save 2.5 months on a 42-year voyage. Everyone who left is still going to die of old age somewhere in the middle of it, and relativity has contributed a long weekend. 20% of light speed. This is Breakthrough Starshot's design figure, and it is worth remembering that Starshot proposed to reach it only for gram-scale chips, pushed by a 100-gigawatt laser array, with no ability whatsoever to slow down at the far end. Gamma is 1.02. A year aboard costs 7.5 days, half the speed of light. There is no propulsion concept with a worked-out mass budget that reaches this. Gamma is 1.15. A year aboard costs about 56 days. Proxima becomes 8.5 years from Earth and 7.4 aboard. And now we hit the first rung where something genuinely dramatic happens, and I want you to notice exactly where it is. At 86.6% of the speed of light, gamma is 2. Exactly 2. 1 year aboard, 2 years at home. This is the first point on the entire ladder where an outsider would say something remarkable is occurring, where a person could go away and come back visibly younger than the friends they left. 86.6% of the speed of light. You have to get more than 5/6 of the way to the ultimate speed limit of the universe before you double your money, and then the floor gives out. At 99% of light speed, gamma is 7. at 99.9% 22, at 99.99 71, at 99.999 224, at 99.9999 707, and at 99.9999999% of the speed of light, 8 nines, gamma is 7,071. 1 year of your life against 7,000 years of everyone else's. Draw that as a graph, and the structure is impossible to miss. From 0 all the way to 86% of light speed, which is to say, across the entire range of speeds that human beings have ever seriously proposed reaching, including all the ones we have no idea how to build, the total benefit is a factor of 2. Everything useful is crammed into the last fraction of a percent, and getting into that last fraction of a percent requires energy that rises without limit as you approach the boundary. It is worth being specific about that wall, because energy rises without limit is the kind of phrase that slides past without leaving a mark. The kinetic energy you have to supply is gamma minus 1, multiplied by the mass, multiplied by the speed of light squared. Put a single ton of payload, a small car, not a starship, a ton, at 10% of light speed, and you need about 453 quadrillion joules. In more visceral units, that is roughly 7,200 Hiroshima bombs, delivered as forward motion into 1 ton. Take the same ton to 20%, and the bill quadruples to something like 29,000. And that is only the accelerating. Nobody in that arithmetic has stopped at the far end. Slowing down is not free and it is not symmetric. A ship that must arrive at rest has to carry the propellant for the braking through the entire acceleration phase, which means it has to accelerate that propellant too, which means it needs more propellant to do that, and the requirement squares. This is why nearly every buildable interstellar concept ever published is a flyby. Not because a flyby is scientifically preferable, because stopping doubles the exponent. Then there is the medium. We talk about interstellar space as a vacuum, and at rest it very nearly is. The local interstellar cloud that the Sun is currently drifting through holds roughly 1/3 of an atom per cubic centimetre, which is a better vacuum than any laboratory on Earth has ever produced. But a vacuum is only a vacuum relative to how fast you're moving through it. At 10% of the speed of light, each one of those single hydrogen atoms arrives at your hull, carrying about 4.7 million electron volts of energy. It stops being a gas and starts being a particle beam, aimed at your face, permanently on, for the duration of the voyage. A dust grain massing 1/10 of a milligram carries the energy of about 11 kilograms of TNT. And there is one more, which I find the strangest of the three. The cosmic microwave background, the leftover glow of the Big Bang filling the entire universe, sitting at 2.725 degrees above absolute zero, so cold and so faint that it took until 1965 for anyone to notice it, gets Doppler shifted as you accelerate into it. Push hard enough for long enough, and that gentle universal whisper blue shifts into a bath of radiation hot enough to melt any material we know how to make. The background temperature of the universe becomes a furnace, not because the universe changed, but because you did. So the steep part of the gamma curve is not just behind an energy wall, it is behind an energy wall, and a particle beam, and a wall of heat, and they all become severe at exactly the speeds where the time compression finally becomes useful. The universe has arranged its obstacles with a certain tidiness. That is why time dilation has never helped anybody. It is not that the effect is weak, it is that the effect is stored somewhere we cannot get to, behind a wall made of energy, and the wall does not have a door in it. And I want to be careful here, because this is the part where the story could end comfortably. It would be very easy to stop at this point and say, relativity offers a shortcut. The shortcut is locked. We cannot reach it. Good night. That would be a tidy video and it would be wrong in an interesting way. Because look again at what gamma actually is. I called it the number of seconds that pass at home for every second that passes aboard. I chose that phrasing deliberately, and it is worth pausing on, because there is another way to say the same thing, and it does not sound like a benefit at all. Gamma is an exchange rate, and every exchange rate has two currencies. When you change money at an airport, you get more of one thing by giving up more of another, and the number on the board tells you the ratio between them. When people describe relativistic travel as saving time, they are quoting the number on the board and forgetting that there is a second currency involved. So here is the question I want to leave hanging, because we are not ready to answer it, and it is going to take the rest of tonight to answer properly. If gamma is an exchange rate, and one side of the exchange is the time you experience aboard the ship, What exactly is the currency on the other side? Hold that. Because before we get to it, I have to show you the version of this where the engineering works, where somebody solves it, where the wall comes down and the numbers become as generous as anyone could possibly want. I have to show you the part where it looks like a gift. Let us assume somebody solves it. I do not know how. Nobody does. But let us grant it, because the interesting part of tonight is not whether the engineering is hard. We have established that the engineering is hard. The interesting part is what the physics actually delivers if the engineering ever stops being the obstacle. So imagine a ship that can hold a steady acceleration of 1 gravity, 9.81 meters per second squared. The same pull you feel right now sitting where you're sitting. Not a burst, not a maneuver, a permanent, gentle, unremarkable 1 gravity, held for as long as anybody wants. The first thing to notice is that this is not a stressful ship to live on. The crew are not strapped into couches enduring anything. They walk around, they put a cup down, and it stays put. They sleep in beds with a floor beneath them and a ceiling above. If you woke up aboard that ship with no windows, you would assume you were in a building. The comfort is the whole reason 1 gravity is the number everyone uses. It is the acceleration a human being can tolerate indefinitely, because we already do, now. The equations for this case are standard, worked out decades ago, and the version most people use lives in the physics FAQ maintained at the University of California, Riverside, written originally by Philip Gibbs and looked after since by John Bayers and Don Cox. They are not controversial. They are the sort of thing a graduate student derives on a Tuesday. Here is what they say. After 1 year aboard that ship, 1.19 years have passed on Earth. You have covered 0.56 light years, you are moving at 77% of the speed of light, and gamma is 1.58. Notice how quickly you got there. 1 year of ordinary, comfortable acceleration, and you're already past 3/4 of light speed. After 2 years aboard, 3.75 years have passed at home. You're 2.9 light years out, at 97% of light speed, gamma 4. After 5 years aboard, 83.7 years have passed at home. You're 82.7 light years from Earth. Gamma is 86. After 8 years aboard, 1,840 years have passed at home, and you are 1,839 light years out. Gamma is 1,895. After 12 years aboard, 113,243 years have passed on Earth, and you have covered 113,242 light years. 12 years. The Milky Way is somewhere between 87 and 100,000 light years across. 12 years of your own life, at 1 comfortable gravity, and you have crossed the galaxy. If you would rather arrive somewhere than flash past it at a fraction under light speed, you flip the ship over at the midpoint and decelerate the rest of the way. That roughly doubles the time you experience on the long trips, because you spend the second half shedding all the compression you gained in the first. And here is that table. The nearest star, 4.3 light years, 3.6 years of your life. Vega, 27 light years, 6.6 years. The center of our own galaxy, 30,000 light years away, where a black hole of 4 million solar masses sits behind so much dust that we have never seen it in visible light. 20 years. The Andromeda Galaxy. 2 million light years. Another galaxy entirely, the nearest large one, the great smudge you can just about see with the naked eye on a dark night if you know exactly where to look. 28 years. 28 years to reach another galaxy. Sit with that, because it is not a trick, and I am not building up to telling you the number is wrong. It is right. A person could leave at 30 and arrive at 58. They would have felt normal weight the entire way. They would have aged normally. No suspended animation, no medical intervention, no generation ship full of descendants who never knew Earth. One person, one career, one working body, and one working mind at the far end, and behind them, 2 million light years. And there is a detail buried in these tables that is genuinely delightful, and I want to give it to you before anything sours, because it is the most counterintuitive good news in physics. That same reference works out what these journeys would look like in a Newtonian universe. A universe with no speed limit at all. A universe where you could hold 1 gravity forever and simply keep going faster, past light speed, past 10 times light speed, without limit. The universe most people instinctively think would be easier to travel in. The nearest star, 4.1 years instead of 3.6. Vega, 10.2 instead of 6.6. The galactic center, 341 years instead of 20. Andromeda, 2,786 years instead of 28. Read those again. A universe with no speed limit would take you 2,700 years to reach Andromeda. Our universe, the one with an absolute unbreakable ceiling on how fast anything can move, gets you there in 28, roughly 100 times faster. The speed limit is not the obstacle. The speed limit is the vehicle. The very rule that stops you going fast is the rule that compresses the journey, and if Einstein had been wrong and Newton had been right, interstellar travel would be far more hopeless than it actually is. There is a way to understand where that 100-fold advantage comes from, and it is worth a minute because it is the cleanest illustration of the odometer idea from earlier. In the Newtonian universe, the ship keeps gaining speed and the journey keeps getting shorter in the ordinary way, but the crew's clocks run at the same rate as everyone else's, so a 2 million light-year trip has to be lived through at whatever pace the ship manages. In our universe, the ship's speed saturates almost immediately. After a year or so, it is essentially pinned against light speed and cannot get meaningfully faster. But the thing that keeps growing, without any limit at all, is gamma. And gamma is not a speed. Gamma is the compression of the crew's own experience. The ship stops going faster and starts going, for want of a better word, thinner. The journey does not shorten because you are quick. It shortens because the geometry folds the road up underneath you. The crew see this directly, in fact, and it is the mirror image of the clock story. From aboard the ship, nobody's clock is running strangely, theirs least of all. What they see is that the distance to the destination has shrunk. At 99.9% of light speed, the 4.2465 light-years to Proxima Centauri measure 0.19 light-years. The gap is genuinely physically shorter in that frame. So the crew's explanation of why they arrived so quickly is not that their clocks cheated, it is that the trip was short, and the two explanations, which sound like they contradict each other, produce exactly the same number of birthdays aboard the ship, which is the internal consistency check that tells you the theory is sound rather than merely strange. I should give you the fuel bill once plainly, and then set it aside because it is not tonight's subject. Assume a perfect engine, one that converts matter directly into light at 100% efficiency, with no waste, an idealization nobody can build. To fly past the nearest star you need 10 kilograms of fuel for every kilogram of ship. To fly past Vega, 57. To reach the galactic center, 62 tons per kilogram. To reach Andromeda, 4,100 tons per kilogram. And if you want to stop when you arrive, 38 kilograms, 886 kilograms, 955,000 tons, and 4.2 thousand million tons per kilogram of payload, with a perfect engine. So no, nobody's doing this next century. But that is an engineering objection, and engineering objections have a way of expiring. This is a physics video, and the physics says the trip is available. The physics says 12 years to cross the galaxy and 28 to another one, and the physics is not going to change. So let us stay inside the good news for a moment longer. Let me put you aboard. It is the end of your second year. You weigh exactly what you weighed at home. The coffee sits flat in the cup. There is a low sound from somewhere behind the wall that you stopped hearing about 8 months ago. You have a routine. You sleep well. Out of the forward window, the stars have crowded together into a bright compressed patch directly ahead. Blue shifted and packed tight, because at 97% of light speed the sky in front of you folds inward. Behind you, the sky has thinned and reddened and gone quiet. There is nothing alarming about any of it. It is beautiful, actually, in the way a weather system is beautiful. 3 years and 9 months have passed on Earth. 2 have passed here. You are 2.9 light-years out, further than the nearest star, and it took 2 years, and you have not missed a night's sleep. Everything is comfortable. Everything is working. The problem that has defeated every generation of our species is, in this imagined moment, simply solved. And this is the moment I have to stop and hand you the receipt. Let us step back for a moment and put the pieces we have on the table, because we are about halfway through, and the shape of the argument is about to change. We started with Voyager 1, half a century out, 1/4% of the way to the nearest star, having accumulated 2.5 seconds of time dilation across its entire mission. We replaced the idea of time as a river with the idea of time as a distance travelled, and we found that in space-time the do-nothing path is the longest one. We went through the evidence, muons falling through your hand right now, clocks on airline seats, satellites detuned in a factory, a staircase step measured to 90 billionths of a second over a lifetime, two brothers 5 milliseconds apart. Then we climbed the gamma ladder and found it flat almost all the way and then vertical. And then we granted the engineering and looked at what a one-gravity ship delivers. 3.6 years to the nearest star, 20 to the centre of the galaxy, 28 to another galaxy entirely. That is where we are. And on the face of it, that is a solved problem. Now here is the receipt. Look at the Andromeda trip again, but this time look at both columns instead of one. 28 years pass aboard the ship. 2 million years pass everywhere else. Not 2 million years for Andromeda. 2 million years for everything. For Earth, for the Sun, for every person the traveller has ever known, and their children, and their children, and roughly 80,000 generations of whatever comes after them. 2 million years ago on this planet, our ancestors were Homo habilis, working stone tools in East Africa. Language had not been invented. Fire had not been controlled. If you had launched that ship 2 million years ago, and it were arriving today, the species that built it would not exist, and the species that received it would have no record of anyone having built anything. That is the second currency. Let me put the exchange rates side by side, because seeing them in a row is what makes the pattern obvious. To Proxima Centauri, stopping at the far end, about 3.5 years aboard, about 6 years at home, a ratio of roughly 1 to 2. That is survivable. That is a long deployment. You come back and your friends are 6 years older, and you're 3.5 years older, and everybody has a slightly odd evening about it and then gets on with their lives. To Vega, 6.5 years aboard, about 27 at home, 1 to 4. You come home and everyone you knew has lived a quarter of a century without you. Your parents may be gone. The children you left are older than you were when you launched. This is already the plot of a tragedy rather than an inconvenience. To the centre of the galaxy, about 20 years aboard, 26,000 years at home, 1 to 1,300. There is no coming home from that in any sense that means anything. 26,000 years ago, the last ice age was near its coldest point, and someone in what is now Austria had recently carved the Venus of Willendorf. If you go to the galactic centre and turn around and come straight back, you return to a planet 52,000 years after you left. Radiocarbon dating cannot reach that far back. There is no institution, no language, no monument, and no genome that lasts that long. And to Andromeda, 28 years aboard, 2.5 million at home, 1 to 87,000. So look at what we have actually bought. Nobody saved any time. Nobody gained a single second of life. The traveller lived 28 years, which is 28 years, which is what 28 years always is. What changed is not the amount of time that existed. What changed is who spent it. Gamma is an exchange rate, and I asked at the end of the last part what the other currency was. Here it is. The other currency is everybody else's existence. You do not compress the journey, you inflate the weight. The 2.5 million years did not vanish because the ship was fast. They happened, in full, to people who were not aboard. There is a smaller version of the same accounting that makes it personal rather than civilizational, and I think it is worth doing because the enormous numbers can go numb quickly. A human life of 80 years contains about 2,500 million seconds. That is your entire supply. Every one of them is spent at the same rate from the inside, whatever you do with them. The Andromeda trip at one gravity with a turnover at the midpoint spends about 900 million of them, more than a third of a life, and returns nothing, because there is nothing to return. The traveller does not arrive with a surplus. They arrive having spent a third of everything they had, in a galaxy where the light they navigated by left before the sun that made it had finished forming planets. And there is an asymmetry in the accounting that nobody mentions, which is that the bill does not stop when the ship does. The traveller who reaches Andromeda and steps out has not merely lost contact with Earth. They have lost the Earth, not the planet. The planet will probably still be there. 2.5 million years is not long by geological standards. What is gone is the version of it they were describing when they said the word. Everything a person means by home is a configuration that lasts decades or centuries, and the ticket price here is measured in units of 1 million years. Let me also be clear about something, because the framing matters. This is not a story about the traveller being cheated by physics. The physics is entirely even-handed. Nobody's running a slow clock and nobody's being punished. Two people simply took different routes through the same geometry, and the routes had different lengths. exactly like the two cars and their odometers. There is no villain in this. There is only a rule about the shape of the road, and the rule happens to be that the road bends away from anyone who accelerates. I want to make sure this lands as a physical fact and not as a mood. Relativity has never given anyone extra time. It cannot. Your own clock reads 1 second per second from the day you are born to the day you die, at any speed, under any acceleration, in any gravitational field without exception. The most relativistically travelled human being in history is roughly 20 milliseconds out of step, and had exactly the same number of seconds in his life as anyone else. What relativity does is redistribute the correspondence. It changes how many of everyone else's seconds go by while you spend yours. And that redistribution is not symmetric, and it is not refundable. It is worth noticing, while we are here, that this asymmetry is also the resolution of the famous puzzle everyone half remembers from school. The twin paradox is usually presented as a contradiction. If all motion is relative, then from the traveller's frame it is the Earth that raced away and came back, so each twin should find the other younger, and that cannot both be true. The way out is not subtle once you see it. The situation is not symmetric because only one of them turned around. Only one of them felt a force. Only one of them had a bent path. Haefel and Keating settled it in 1971 by physically flying the clocks and physically bringing them back, and the clocks physically disagreed, in the direction and by the amount that the bending of one path predicted. There is no paradox. There is only a road with a corner in it, and whoever takes the corner arrives with a smaller number on the odometer. This is the first of the 4 walls, and I will name it plainly so we can keep track. The first wall is that the receipt is written in a currency you do not own. Every hour you save is taken from someone who did not agree to the transaction, and the further you go, the more of them there are. Now I can already hear the sensible objection, and it is a good one. So what? This is a known cost. Explorers have always left people behind. Sailors did not see their families for years, and the families managed, and the sailors came home to changed houses and got on with it. Emigration is exactly this. You leave, the world you left continues without you, and you accept it. Why is this different other than by being larger? It is a fair question, and it has an answer, and the answer is the reason this video exists. The difference is that all of those departures, every sailor, every emigrant, every explorer, kept one thing: they kept a shared present. The sailor at sea and the family at home were, at every moment, both alive in the same now. They could not talk, but there was a fact of the matter about what the other was doing at any given instant. The letter that took 6 months to arrive still described something that had happened, definitely, on a Tuesday, and the Tuesday was the same Tuesday for both of them. That is the thing interstellar space takes away, and it does not take it away by being far, and it does not need a spaceship to do it, and it has already happened. There is no meanwhile. I want to ask you a question that sounds trivial and is not. What is happening right now on Proxima Centauri? You do not know the answer, obviously, or nobody does. It is 4.25 light years away, and the light we are receiving from it left in the spring of 2022. But that is not what I am asking. I am not asking whether you know. I am asking whether there is an answer, whether out there in the dark at this instant something definite is occurring, and the only problem is that we cannot see it yet. Everyone's instinct says yes. Of course there is. The star is there. It is doing something. The something is happening now, and the news is simply slow. That is how we think about distance and always have. A letter takes 6 months to cross an ocean, but the thing it describes happened on a specific day, and both ends of the correspondence agree about which day it was. Relativity says no, not we cannot know, not the information is delayed. It says the question has no answer, because now over there is not a property of the universe, it is a property of your velocity. And 2 people standing next to each other, moving at different speeds, will disagree about what is happening at a distance, genuinely disagree both correctly with no possible way to settle it. This is the piece almost nobody talks about. Time dilation gets all the attention, length contraction gets a diagram in the textbook, and the relativity of simultaneity, which is the strangest of the 3 and by some distance the most consequential, gets a paragraph and a footnote. It is also worth saying that this is not a fringe reading of the theory, or a philosopher's embellishment. The relativity of simultaneity is not a consequence of special relativity. It is one of its foundations. It falls directly out of the 2 postulates Einstein started with in 1905. that the laws of physics are the same in every non-accelerating frame, and that the speed of light is the same for everybody regardless of how they are moving. Hold both of those at once, and a shared universal present becomes mathematically impossible, because at the same time would have to be defined by signals, and every signal travels at a speed that everybody measures differently in every other respect, and identically in this one. Einstein saw this before he saw time dilation. Simultaneity was the first casualty, not the last. So let us build it properly, because once you see it, you cannot unsee it. Start with what now means. When you say right now, you are describing a slice through the universe, an enormous three-dimensional sheet containing every event you consider to be happening at this moment. Your bedroom, the far side of the planet, the surface of the sun, the stars, everything, all cut at one instant. Physicists call this a plane of simultaneity, and everybody carries one around. It is your personal definition of the present. Now the crucial part. That plane is not fixed. Its orientation depends on how fast you're moving. When you change speed, your plane of simultaneity tilts. The tilt is minuscule. It is so small that at ordinary distances nothing perceptible happens. But a tilt has a lever arm, and the lever arm here is distance. Tilt a plank by a fraction of a degree and the far end barely moves, unless the plank is enormous, in which case the far end moves a very long way indeed. Interstellar distances are the enormous plank. There is an image that helps here, and I want to offer it because the phrase plane of simultaneity is doing a lot of work and it is very abstract. Think of the history of the universe as an infinitely tall stack of paper, one sheet for each instant, every sheet containing everything that exists at that moment. Your experience of the present is a single sheet being pulled out of the stack. What relativity says is that the stack does not come with the sheets pre-cut. Different observers slice it at different angles and each of them gets a perfectly good sheet, and no two of their sheets contain quite the same events. The stack is real. The cutting is not. There is no correct way to cut it, and the universe does not do it for you. Now think about what happens when the sheet is tilted rather than flat. Near you, the tilt makes almost no difference. The sheet passes through your room within a nanosecond of horizontal. But follow the sheet outward, kilometre after kilometre, light year after light year, and the small angle compounds into an enormous vertical displacement. By the time your sheet reaches Proxima Centauri, it has drifted noticeably up or down the stack. By the time it reaches another galaxy, it has drifted through centuries of that galaxy's history. Same tilt, longer plank, and nothing about you feels different. You do not sense the sheet moving. Nobody has ever felt their plane of simultaneity rotate, because there is nothing to feel. The rotation is a fact about the relationship between you and everything distant, not a fact about you. The formula is simple enough that I can give it to you out loud and you will remember it. The offset between two observers' definitions of now at some distant place is equal to the relative velocity, multiplied by the distance, divided by the speed of light squared. Velocity times distance over c squared. That is all of it. And I want to point out something about that formula, which is the reason this wall is so different from the others. Look at where the velocity sits. It is on top by itself to the first power. Time dilation and length contraction both depend on velocity squared over the speed of a light squared, which is why they are invisible until you get close to light speed. Square a small number and you get a much smaller number. But simultaneity is first order. The velocity is not squared. It does not get crushed. It just sits there, multiplied by a distance that can be as large as you like. Which means this effect does not need a spaceship. It does not need a percentage of light speed. It does not need any technology that does not exist. It needs walking. Roger Penrose made this famous in 1989 in a book called The Emperor's New Mind, where he used it to illustrate an argument that two philosophers, Cornelis Reitdijk and Hilary Putnam, had made independently in the 60s. His setup was two people passing each other on a street, one walking toward the Andromeda Galaxy, one walking away from it. Ordinary people, ordinary pace, ordinary afternoon. Their definitions of what is happening in Andromeda at that instant differ by days. I'm going to give you the full arithmetic in a moment, and I want to warn you in advance that the numbers get worse than you're expecting. But before we get there, I want to make sure the logical structure is clear because the numbers are meaningless without it. There is no umpire. That is the thing. When two observers disagree about the simultaneity of distant events, there is no third observer who is actually right. relativity's entire content, the thing Einstein was insisting on in 1905, is that no frame of reference is privileged. Every plane of simultaneity is exactly as valid as every other. So when the person walking north and the person walking south disagree about what is happening in Andromeda, they are not making an error that better instruments would fix. They are both correct, and the disagreement is not resolvable because there is nothing to resolve it against. There is a second thing worth saying in fairness, and it is the reason this has stayed obscure. You cannot use the disagreement for anything. You cannot walk quickly toward a star and thereby learn what is happening there sooner. Everything on your tilted plane of simultaneity is outside your light cone, causally unreachable, unable to affect you or be affected by you in either direction. The disagreement has no operational consequence whatsoever. Nothing measurable changes. No experiment detects it. Nobody wins anything, which is precisely what makes it so easy to file under harmless curiosity and forget about. It costs nothing. It changes nothing. It just quietly removes the assumption that there is a shared present tense, and then hands you back a universe that looks exactly the same as it did before. And that assumption, it turns out, was doing an enormous amount of work, because everything a human being means by we is built on it. A conversation assumes both parties are in the same now. A promise assumes it. A marriage, a contract, a war, a civilization, the entire idea of two people being alive at the same time. All of it rests on the belief that there is a fact of the matter about what is happening elsewhere while you are here. Relativity does not say that belief is wrong. It says it is local. It works here, in this room, on this planet, because everything you have ever loved has been within a fraction of a light second of you, moving at a few meters per second. Under those conditions, the disagreement is nanoseconds and nobody notices. Change either condition and it stops working, and you do not have to change them much. Let me show you the numbers. Let us start close to home with the nearest star, and let us start with the slowest thing a person can do. Proxima Centauri sits 4.2465 light-years away. Walk toward it at an ordinary pace, 1.4 meters per second, which is a comfortable stroll, the speed you move down a corridor without thinking about it. And your definition of now at Proxima shifts by 0.63 seconds compared to somebody standing still. Turn around, walk the other way at the same pace, the shift flips sign. So the difference between your notion of the present at Proxima Centauri while walking toward it and your notion of the present at Proxima Centauri while walking away from it is 1.25 seconds. That is walking. That is what a human body does with no equipment at all. Get in a car, 100 kilometers per hour, an ordinary motorway speed. Your definition of now at Proxima shifts by 12.4 seconds. And here is the version of that number that I find genuinely difficult to hold. Two cars pass each other in opposite directions on a motorway. The gap between them is a couple of meters and it lasts about 1/10 of a second. In that 1/10 of a second, those two drivers, neither of whom is doing anything remarkable, both of whom are probably thinking about lunch, disagree about what is happening at the nearest star by nearly 25 seconds. Take an aircraft, 900 kilometers per hour, 1.9 minutes. Go up to the International Space Station, 7.66 kilometers per second, 57 minutes. An astronaut's present moment at Proxima Centauri differs from yours by nearly an hour, and the difference reverses every 45 minutes as they come round the other side of the planet. And now, the one that does not require anybody to go anywhere. The Earth moves around the Sun at 29.78 kilometers per second. You're doing that right now, and you have never stopped. That motion shifts your definition of now at Proxima Centauri by 3.7 hours. And 6 months from now, the Earth will be on the other side of its orbit, travelling in exactly the opposite direction. Which means that your own personal definition of what is happening at the nearest star swings back and forth through a range of 7.4 hours every single year for your entire life, because you live on a planet that goes around a sun. You have never once had a stable answer to the question, what is happening at Proxima Centauri right now? You have had a slowly oscillating answer with an amplitude of several hours, and nobody ever mentioned it. Now let us go further out, because the lever arm gets longer. The centre of our galaxy is about 26,000 light-years away. At walking pace, 1.4 meters per second, your definition of now at the galactic centre shifts by 1.06 hours. Stand up, walk across the room to make a cup of tea. In the time it takes to cross the carpet, the present moment at the centre of the Milky Way has moved by more than an hour, and it will move back when you sit down. In a car at motorway speed, 21 hours, nearly a day. On an aircraft, 7.9 days. 2 passengers on 2 aircraft passing over the Atlantic in opposite directions disagree about the state of the galactic centre by more than 2 weeks. From the Earth's orbital motion alone, 2.6 years, with a 6-month swing of 5.2 years. Since the day you were born, your definition of the present at the centre of our own galaxy has been oscillating through more than 5 years of that place's history, twice a year, without pause, without your involvement, and without any possibility of your noticing. And the Sun itself is moving around the galaxy at about 230 kilometers per second, which shifts the galactic centre's present by about 20 years. There are 2 intermediate stops worth putting on the ladder, because they show how smoothly the effect scales. Sirius, the brightest star in our sky, is 8.6 light-years out. At walking pace, the shift there is 1.27 seconds. From the Earth's orbital motion, 7.5 hours. Vega, 25 light-years away, the star Hafael and Keating's contemporaries were using as a calibration source, and the one Carl Sagan chose as the origin of the message in contact. 3.68 seconds at walking pace, 11 minutes on an aircraft, nearly 22 hours from Earth's orbit alone. There is nothing special about any of these distances. The effect simply scales, linearly, with how far away the thing is, and space is very good at providing distance. The reason none of this shows up in daily life is the other end of the same scaling. At the distance of the Moon, walking pace shifts the present by about 1.8 nanoseconds. At the distance of the far side of this room, it is unmeasurable by any instrument that exists. The universe is not being subtle here. It is simply that we have spent our entire species' history confined to a region where the lever arm is far too short to lift anything. And then there is Andromeda, 2.5 million light-years, the nearest large galaxy. On a properly dark night, away from towns, you can see it with your own eyes as a faint smudge in the constellation Andromeda, the most distant object visible to the unaided human eye, about 1 trillion stars, arriving as a grey blur you could cover with a thumbnail. Walking pace, 4.26 days. That is Penrose's number, worked out exactly. 2 people passing on a pavement, one walking toward Andromeda and one away, differ in their definition of that galaxy's present by 4.25 days. I want to do that one properly, because it is the moment the whole thing becomes real. Picture an ordinary afternoon outside an ordinary shop. It is not raining. There is a door that sticks slightly and makes a sound when it closes. 2 people are walking past each other on the pavement, one carrying a bag, one with their hands in their pockets, both moving at about 1.5 meters per second in opposite directions. They do not look at each other. Neither of them has any reason to remember this moment for the rest of their lives. At the instant they draw level, one of them believes that a certain event in the Andromeda Galaxy is happening now. The other believes that the same event happened 4 days ago. 4 days. Not 4 seconds, not 4 minutes. 4 days of the history of 1 trillion stars. There is no third person who could tell them which of them is right, because neither of them is wrong, and there is no fact of the matter for anyone to be right about. And they do not break stride. Neither of them notices. Neither of them ever will. Keep going. In a car at 100 kilometers per hour, 84.6 days. On an aircraft, 2.1 years. On the International Space Station, 63.9 years. An astronaut's definition of the present in Andromeda differs from yours by roughly a human lifetime, purely because they are in orbit and you are not, and from the Earth's orbital motion alone, 248 years, 6-month swing, 497 years. Let me say that one slowly, because it is the number I would most like you to keep. Nobody has launched anything. Nobody has accelerated anything. Nobody has built anything. Simply by living on a planet that orbits a star at 30 kilometers per second, your personal definition of what is happening right now in the Andromeda Galaxy sweeps back and forth across 5 centuries of that galaxy's history twice every year for as long as you live. 500 years of another galaxy's existence, in and out of your present tense, on an annual cycle, while you go about your day. And the Sun's motion around the Milky Way pushes that to 1900 years. It is also worth remembering that the Earth's orbital speed is not the largest number available. The Sun is moving at about 370 kilometers per second relative to the rest frame of the cosmic microwave background, and the local group of galaxies as a whole is moving at around 620 kilometers per second towards something in the direction of Centaurus that astronomers call the Great Attractor. Plug those into the same formula and the offsets at Andromeda's distance run into thousands of years. There is no version of you that is standing still, and there never has been. And I want to close one loophole before somebody reaches for it, because it is the natural objection, and it is worth answering honestly. You might say, fine, but this is a bookkeeping artifact. The events in Andromeda are happening whenever they are happening, and the two pedestrians are simply using different labelling conventions, like two people using different time zones. Nobody thinks London and Tokyo are living in different realities. The trouble with that answer is that time zones have an underlying truth they are conventions about. When it is noon in London and 9 in the evening in Tokyo, there is still a single physical instant that both labels refer to, and you can prove it by putting the two people on a telephone. There is no telephone here. There is no underlying instant that the two pedestrians' labels are conventions about, because the only thing that could establish one would be a signal, and every signal is limited by the same speed that produced the disagreement in the first place. The convention goes all the way down. That is the difference, and it is not a small one. So here is what the second wall actually is, and I want to state it as plainly as I can. Interstellar space does not merely make communication slow, it dissolves the present tense. Past a certain separation, what is happening there right now stops being a difficult question and becomes a question with no referent. A question like, what is north of the North Pole, which sounds perfectly grammatical and has no answer. And the terrible elegance of it is this. This wall did not close when someone launched a ship. It does not require any technology at all. It is a property of interstellar distance itself, and it has been in place since before there were people to walk past each other on pavements. It was closed this morning. It is closed right now. It is closed for Voyager 1, drifting out there at one light day, entirely unaware. Which means that when the first traveller finally leaves for another star, they will not be losing a shared present at the moment of departure. They will simply be finding out that they never had one. There is a third wall, and it is the most ordinary one, and it is the reason the first two ever come to matter to a human being rather than to a physicist. This wall requires no relativity at all. It has nothing to do with gamma or simultaneity or planes tilting. It is simply the speed of light, applied to conversation. Every exchange between two people has a minimum round-trip time set by how far apart they are. Question out, answer back. And because that time is fixed by physics rather than by patience, there is a distance past which conversation stops being possible. Not difficult, not slow, but structurally impossible, because a conversation requires that a reply still be a reply to the thing it answers. Let me walk you out from here. Two people in a room. The light travel time between them is a few nanoseconds. You will never detect it. Conversation is effortless, and the delay is not merely invisible, it is smaller than the reaction time of a nerve. Earth to the Moon, 1.28 seconds each way, 2.5 seconds for a round trip. This is awkward, and if you have ever listened to Apollo transmissions, you have heard the awkwardness, the small pause before every answer, the tendency of both parties to talk over each other. But it works. 12 people stood on the moon and had conversations with Houston, and the conversations were conversations. Earth to Mars, between about 3 and 22 minutes each way, depending on where the two planets are in their orbits. This does not work. You cannot have a conversation with a 22-minute gap between sentences. This is why every Mars mission is run by uploading a sequence of instructions and then waiting, and why the rovers have to be able to handle surprises by themselves. Mars is the distance at which human beings stopped being able to talk to their machines and started having to write to them. Earth to Voyager 1, from November of this year, 24 hours each way, 48 hours for a round trip. If you and I were separated by that distance, and we tried to have a 10-line exchange, it would take 20 days. Not because either of us was busy, because that is how long the light takes. Earth to Proxima Centauri, 4.2465 years each way, 8.5 years for a round trip. Ask a question on your 20th birthday and the answer arrives shortly before your 29th. Everything you were when you asked it will have changed by the time it comes back. The person who receives the answer is not, in any meaningful sense, the person who sent the question. Earth to the center of the galaxy, 26,000 years each way. The round trip is 52,000 years, which is roughly twice the entire span of settled human civilization and slightly beyond the reach of radiocarbon dating. You would not be sending a message, you would be leaving a deposit. There is a physical wall stacked on top of the geometric one, and it is worth a moment because it is the reason the ladder above is optimistic rather than pessimistic. Signal strength falls with the square of distance. Voyager 1 currently transmits to us at about 160 bits per second, slower than a telephone modem from the 1980s, from a transmitter putting out roughly the power of a refrigerator light bulb, received by dishes 70 meters across. Move that same transmitter out to Proxima Centauri, and the signal arrives about 2.4 million times weaker. Everything on the interstellar communication ladder assumes not only that you are willing to wait, but that somebody has built an antenna capable of hearing a whisper across a distance where the whisper has been thinned to almost nothing. We have tried the outgoing version exactly once with any real power behind it. In 1974, the Arecibo Observatory in Puerto Rico transmitted a 3-minute message toward the globular cluster Messier 13, 25,000 light-years away, encoding the numbers 1 to 10, the atoms of life, a strand of DNA, a human figure, the solar system, and a picture of the telescope itself. Nobody involved thought a reply was coming. The round trip is 50,000 years. The team said so at the time. It was a demonstration of what the rebuilt dish could do, not an attempt at contact. And I want to name what actually breaks along that ladder, because it is not simply that things get slower. Somewhere between the Moon and Mars, human beings lose the ability to talk to each other and retain only the ability to write to each other. That is a real threshold, and it is closer than most people think. It is inside our own solar system, and we have already crossed it. Somewhere past Proxima Centauri, they lose the ability to write and retain only the ability to leave records. A letter is still a letter if the reply takes a year. It stops being a letter when the reply takes longer than the correspondent's lives. At that point you are not writing to a person. You are writing to a posterity, and posterity does not write back. And there is a structural problem underneath all of this that has nothing to do with signal strength, which is that a conversation is not merely a sequence of messages. It is a sequence of messages in which each one can still change what the next one says. That is the whole function. When the round trip exceeds the timescale on which the situation changes, the exchange stops being a conversation even if every message arrives perfectly. Mission controllers know this precisely. The reason Mars rovers carry autonomy is not that the signal is weak, but that by the time an instruction arrives, the thing it was an instruction about has already happened. And this brings us to the piece of this that I find genuinely difficult, which is what happens when you put the relativistic ship back into the picture. Remember the traveller at 1 gravity, 12 years to cross the galaxy, 113,000 years passing at home. Now think about what mail looks like on that ship. The traveller sends a message home. That message travels at the speed of light, from a ship that is moving at a fraction under the speed of light in the same direction the message came from, and it arrives. Slowly, enormously delayed, but it arrives. Earth can hear the ship. Earth will always be able to hear the ship, for as long as the transmitter works and somebody is listening, which will not be long, because the somebody is going to be replaced by another somebody about 4,000 times before the ship reaches the far side of the galaxy. Now the other direction. Earth sends a message to the ship. The message leaves at the speed of light and begins to chase a vessel that is already moving at 97% of light speed and is still accelerating. That chase is the subject of the next part, and it does not end the way you would expect. But even before we get there, notice the asymmetry, because it is cruel in a very specific way. The channel is not symmetrical. The traveller can always speak. The traveller cannot always be answered, which means the relationship between a relativistic ship and the world it left is not a conversation that gets slower and slower until it stops. It is a broadcast into a silence, a person able to talk indefinitely to a home that is no longer capable of replying, and, crucially, unable to tell the difference between a home that has stopped answering and a home that is answering into a void. There is one more piece of this worth putting on the table, because it is the closest thing to a hopeful note in the entire structure, and it is also the most melancholy fact in the whole subject. The Voyager Golden Record is the honest version of interstellar communication. When they were designing it in 1977, Carl Sagan's committee did not build a transmitter or a beacon or a relay. They made an object, a gold-plated copper phonograph record with greetings in 55 languages, the sound of a heartbeat, a kiss, thunder, a mother speaking to her child, Bach and Chuck Berry and a Navajo night chant, and instructions for playing it engraved on the cover in a diagram that assumes nothing about the reader, except that they understand hydrogen. Nobody involved expected an answer. The record was not sent in the hope of an exchange. It was built in full knowledge that the distances involved make exchange impossible, and so instead of a message they made an artifact, something that does not need to be replied to in order to have been worth sending. It will still be legible in 1 billion years because there is nothing out there to erode it. That is what communication looks like on the far side of the third wall. Not correspondence, archaeology, sent forward. And now we have to talk about the chase, because there is a signal leaving Earth right now in this story, aimed at a ship that is pulling away at 1 gravity, and the question is whether it ever arrives. The answer is one of the strangest facts in physics. I have been holding this one back all night, and I want to tell you where I found it, because the location is part of the story. Everything I gave you in Part 5, the 12 years to cross the galaxy, the 28 to Andromeda, the tables that make interstellar travel look solved, comes from a single reference page. It is a well-known page. Physicists send students to it, and 2 sections further down that same page, under a heading that reads, almost casually, "Below the rocket, something strange is happening is the fact I'm about to give you. It is not obscure, it is not disputed. It has been sitting in plain sight in the same document as the good news for 30 years, and almost nobody who quotes the good news ever scrolls that far. Here it is. An observer who holds a constant acceleration develops a horizon behind them. Not a metaphorical horizon, not a practical limit or a communications difficulty. A horizon in the technical sense, the same sense the word carries at a black hole. A surface beyond which no signal can ever reach you, no matter how long you wait, no matter how much power the transmitter has, for the entire remaining future of the universe. And you do not need a black hole to make one. You do not need mass. You do not need curved space-time. You need an engine. The horizon sits at a fixed distance behind the ship, and the distance is the speed of light squared, divided by your acceleration. For a comfortable 1 gravity, that comes out to 9.16 trillion kilometers. In more useful units, 0.9687 light-years, just under 1 light-year, directly behind you, permanently. It does not recede as you speed up. It does not fall further behind. It follows you at that fixed remove for exactly as long as you keep the engine running, like a wall you are towing. This thing has a name, incidentally, and a whole body of theory behind it. It is called the Rindler Horizon, after Wolfgang Rindler, the physicist who worked out the coordinate system that an accelerating observer naturally uses. And the mathematics of that coordinate system is not merely similar to the mathematics of the region just outside a black hole. It has the same structure, term for term, which is exactly what Einstein's equivalence principle demands. If there is genuinely no local difference between standing in a gravitational field and sitting in an accelerating rocket, then whatever a gravitational field can do to time and causality, an accelerating rocket must be able to do as well. The rocket does not merely resemble gravity. As far as the local physics is concerned, it is gravity. There is a further consequence that most people find hard to believe on first hearing. In 1976, William Unruh showed that an accelerating observer should detect thermal radiation coming from their own horizon, at a temperature proportional to the acceleration. The horizon is not just a causal boundary, it glows in exactly the way a black hole's horizon glows. At 1 gravity, the temperature works out to about 0.04 of a quintillionth of a degree above absolute zero. Utterly, hopelessly undetectable, roughly 10 billion times colder than the leftover heat of the Big Bang. But it is not zero. The wall behind an accelerating starship is, in the strict thermodynamic sense, a real object with a temperature. Now let me tell you what it looks like, because that is the part that stays with you. You are 2 months out. The engine is holding a steady 1 gravity and you have stopped noticing it. You go to the back of the ship where there is a window and you look at the sky behind you. At first there is nothing to see. Earth's sun is a bright star among other bright stars, a little redder than you remember, a little dimmer, and you put that down to distance. 6 months out it has changed. The whole hemisphere behind the ship has taken on a colour. The stars back there have slid toward red, and they are not just dimmer, they are dimming. Slowly, continuously, in a way that distance alone does not explain, and they have begun to slow. Not their motion, their aging. A variable star behind you that used to pulse every 4 days now takes 5, then 6, then 8. The clock of everything behind the ship is winding down. A year out, and there is a region of the sky back there where nothing is arriving from at all. It is not black in the way empty space is black. It is a surface, and things are falling onto it. Every star behind you is drifting toward it, reddening as it goes, fading, freezing, and finally sliding out of visibility altogether. Not moving away, but piling up against a plane that is not made of anything, that has no substance, that no instrument on board can detect except by the absence of everything on the far side. That is a black hole's event horizon. Every property of it, the redshift, the dimming, the apparent freezing of time on the surface, the absolute causal cutoff, is exactly what you would see falling toward one. And it has been manufactured out of nothing but your own engine, in perfectly flat, perfectly empty, perfectly unremarkable space with no mass anywhere near it. Now for the number that actually matters, because the distance version is unsettling, and the time version is worse. Any signal sent from your departure point later than the speed of light divided by your acceleration will never catch you. At 1 gravity, that quantity is 30,570,000 seconds, 353.8 days, 354 days, under a year. Let me put that into words that mean something. If you leave Earth on a ship holding a steady 1 gravity, and you keep holding it, then Earth has approximately 11 months and 20 days to say anything to you at all. A message transmitted on day 353 will, eventually, after an extraordinarily long chase, catch you. A message transmitted on day 355 will chase you for the rest of time and never arrive. Not late, never. Those photons are emitted, they travel at the speed of light forever, they never slow down, they never stop, and the gap between them and the ship converges to a value they cannot close. I want to make sure the strangeness of that is clear, because it sounds like it should be impossible. The ship never reaches the speed of light. Light is always faster than the ship at every single instant by a comfortable margin, and yet the light loses. It loses because the ship is not moving at a constant speed. It is accelerating forever, and the small head start that light has at every moment is spent closing a gap that the acceleration has already widened. It is Zeno's race run in reverse. The pursuer is always faster, and the gap still never closes. And notice where the ship actually is when the door shuts. 354 days out at 1 gravity, the ship is about half a light year from home. It has not reached the nearest star. It has not reached 1/10 of the way to the nearest star. It has not even left the sun's own gravitational neighborhood. The outer Oort cloud, the shell of comets that still orbits our star, extends out to something like 1.5 light years. The traveller is still inside the solar system, in every meaningful sense, when the last message that will ever reach them is sent. There is one more thing that happens back there which I find quietly horrible, and it follows from the same geometry. Because the ship's plane of simultaneity is sweeping as it accelerates, a distant object behind the ship does not simply recede. It behaves impossibly. The same reference page works through the case. A star behind an accelerating observer appears to move away, slow down, stop, and then fall back toward the ship. Motion that no force acting on that star could produce. Motion that would be a violation of physics if anything were actually doing it. Nothing is. The star is sitting there, minding its own business, moving as it always has. What is moving is the observer's definition of when the star is, sweeping along the star's history like a searchlight. Everything the traveller sees behind them is a report about their own path, dressed up as news about the universe. Now I owe you 2 caveats, because this is a channel about what is actually true, and both of them matter. The first is that the horizon exists only while the acceleration continues. Shut the engine off and it dissolves, and the backlog of messages that have been stacking up against it comes flooding in. The wall is not permanent, it is conditional. But look at what the condition is. A 1-gravity ship that stops accelerating is not a 1-gravity ship anymore. The entire compression, the 12 years to cross the galaxy, the 28 to Andromeda, comes from holding that acceleration without interruption. The moment you switch off to listen, you have surrendered the thing that made the trip possible. The horizon is not a side effect of the deal. It is the price of the deal, and you cannot keep the deal and refuse the price. The second caveat is that the horizon is observer-dependent. It is not out there in the universe. Nothing dramatic happens at that plane for anybody else. Earth notices nothing. The messages are real. They are travelling perfectly normally, and to any observer who is not accelerating, there is no wall anywhere in the sky. The horizon is a fact about your world line and nobody else's. which is not the reassurance it sounds like, because it means this is a private cage made out of your own path through space-time, invisible to everyone who might otherwise notice that you had stopped receiving. They keep sending. They have no way of knowing. From Earth, the ship simply goes quiet in the ordinary way that distant things do, and there is no signal, no alarm, no discontinuity, nothing that distinguishes a traveller who has fallen behind a horizon from one who has simply gone far away. And there is one last twist, which is the piece that closes off the obvious escape. You might reasonably think, fine, then accelerate harder, get there faster, take the punishment, cut the trip down, minimize the exposure. The horizon distance is the speed of light squared divided by your acceleration. The acceleration is on the bottom. At 10 gravities, brutal, survivable only briefly, the sort of thing a fighter pilot endures for seconds, the horizon closes from 0.97 light-years to 0.097, and the cutoff falls from 354 days to 35. At 100 gravities, the wall is 1/100th of a light-year behind you, and Earth has 3.5 days to say goodbye. Push harder, and the door shuts sooner. There is no setting on the dial that gives you both. The dial trades speed against contact monotonically all the way down, with no optimum and no clever compromise. So here is the third wall, stated plainly. The thing that seals you in is not the distance. It is not the emptiness. It is not even the speed. It is the engine, the single instrument you built to escape, doing exactly what you asked it to do, and closing the door behind you as it goes. And we still have not answered the question we started with. We have 3 walls and no explanation of why they all exist. So let us try the last obvious escape and see what it costs to turn around. So let us try to get out. We have 3 walls. The receipt is written in somebody else's currency. The present tense does not extend across a light year, and the engine that shortens the trip seals the door behind you. Each of those is bad. None of them is obviously fatal, because there is one move we have not tried yet, and it is the move everybody reaches for. Turn around, come home. The first thing that turning around costs you is fuel, and the arithmetic here is worse than almost anyone expects, so let me do it carefully. Take 2 travellers heading for Vega, 27 light-years away, both under 1 gravity. The first flies past without stopping. The second decelerates at the midpoint and arrives at rest. Assume both are using a perfect engine, a photon drive converting matter directly into light with no waste at all, which is not a thing anybody can build but which sets a hard lower bound on what is possible. The one who flies past needs 57 kilograms of fuel per kilogram of ship. The one who stops needs 886, 15 times as much, for the same destination, at the same acceleration, over the same distance. And the reason is a problem the Apollo engineers knew intimately, which is that fuel is payload. The propellant you will need for braking has to be carried through the entire acceleration phase, which means it has to be accelerated too, which means you need more propellant to accelerate it, which means more still to accelerate that. The requirement does not add. It compounds. It is worth putting the whole fuel table in front of you once, because the shape of it says something the individual numbers do not. With a perfect photon engine, flying past the nearest star costs 10 kilograms of fuel for each kilogram of ship. Flying past Vega, 57. Reaching the galactic center, 62 tons per kilogram. Reaching Andromeda, 4,100 tons per kilogram. Now the stopping column, 38 kilograms, 886 kilograms, 955,000 tons, and 4.2 thousand million tons per kilogram of payload. The gap between the 2 columns widens by orders of magnitude as the distance grows, which means that the further you go, the more disproportionately expensive it becomes to arrive rather than merely to pass. And there is a small, human detail buried in the reason why. The traveller who flies past Vega takes about 28 years of Earth time and ages 3.9 years. The traveller who stops takes 29 years of Earth time and ages 6.6. They arrive within a year of each other by the outside world's clock. But the one who stopped had to run their engine for almost twice as long in their own experience, and everything about the fuel bill follows from that single fact. Braking is not the reverse of accelerating. Braking is more accelerating, pointed the other way, and it costs exactly what accelerating costs. Which is why every serious interstellar mission concept anyone has ever published is a flyby. Not because a flyby is scientifically preferable. A flyby gives you a few hours of data after a voyage of decades. It is because stopping doubles the exponent, and the exponent was already the problem, and that is only stopping. Coming home means stopping, turning, accelerating all the way back and stopping again. 4 legs instead of 2, with the fuel for each leg carried through all the legs before it. The numbers stop being numbers and become the sort of expression you write down once and then quietly put away. The second thing that turning around costs you is that the universe ahead of you gets hot. I mentioned this earlier and it deserves its full weight now. The cosmic microwave background is the leftover glow of the early universe. It is everywhere. It is 2.725 degrees above absolute zero, and it is the coldest thing in nature. So cold and so faint that when Penzias and Wilson accidentally detected it in 1965, they spent months checking whether it was pigeon droppings in the antenna. Accelerate into it and it blue shifts. And because you are accelerating without limit, the blue shift grows without limit. After a few years of holding one gravity, that whisper of leftover warmth has been compressed into a bath of radiation hot enough to melt every material we know how to make. There is something almost unfair about that. The traveller is not running into anything. They are not colliding with a star or crossing a dust lane. They are flying through the emptiest available volume of the universe, and the emptiness itself has caught fire, because they went fast enough that the coldest thing in existence became the hottest thing in the cabin. The third thing that turning around costs you is the point of the exercise, and this is the one I want to spend the most time on. Suppose you solve the fuel and you solve the shielding. Suppose the traveller goes to the galactic centre, turns around and comes home. 20 years out, 20 years back. 40 years of a life. Long, but survivable. A person could leave at 25 and be home by 65. They arrive on an Earth 52,000 years after they left. Not 52,000 years of waiting. 52,000 years of history. Everything that has happened in the whole of recorded time, every language, every nation, every religion, every book, every war, every city, fits inside the last 6,000 of those years, about 1/9 of the trip. 52,000 years ago there were Neanderthals. The Venus of Willendorf, one of the oldest carved figures anyone has found, is younger than that gap by more than 20,000 years. Radiocarbon dating does not reliably reach that far back. The traveller would return to a period their own civilization could not have dated. So the return does not restore anything. That is the entire point. The traveller has not been away and come back. They have moved forward, and there is no direction in this geometry that undoes it. And here is the reason that is not merely sad but structural, and it is the thing that turns 3 separate problems into one. Coming back does not reverse the cost, it doubles it. The outbound leg subtracted from the traveller's clock relative to Earth. The homebound leg does not add any of it back, it subtracts again. There is no route, no manoeuvre, no clever trajectory that runs the meter backwards, because the meter is measuring the length of a path, and paths do not have negative lengths. Every additional kilometre of the journey, outbound, homebound, sideways, looping, anything, makes the traveller's total elapsed time smaller relative to the people who stayed still. This is worth being precise about, because it is where a lot of people's intuition finally gives way. You might think that if the outbound trip made you younger, the return trip should make you older again by symmetry. The way walking east and then west leaves you where you started. It does not work like that, and the reason is the minus sign I mentioned in part 2. In ordinary geometry, going out and coming back returns you to the origin. In space-time geometry, going out and coming back returns you to the same place. But the time coordinate has only ever run one way, and the length you accumulated along the path is a total that only grows. It is just that it grows more slowly than it would have if you had stayed put. You cannot come home, not because home is far away, because the operation you would need does not exist. Now, at this point, somebody always asks about the exotic exits, and they deserve a straight answer, so let me give one. Faster-than-light travel, in the form of the Alcubierre warp metric published in 1994, is a legitimate solution of Einstein's field equations. It requires a region of negative energy density, and quantum inequalities appear to forbid the quantities needed. The more recent work by Bobrick and Martier in 2021, and the positive energy geometries that followed it, is real physics, and is worth taking seriously. And all of it is strictly slower than light. It reshapes the ride. It does not raise the ceiling. Traversable wormholes need the same exotic matter nobody has found. But here is the part that matters for tonight, and it is not usually said. Even a working faster-than-light drive would not touch 2 of our 3 walls. It would not restore a shared present. It would make simultaneity worse, because in relativity any genuine faster-than-light signal is, in some perfectly ordinary frame of reference, a signal travelling into the past, which is why you cannot have superluminal messaging and cause and effect at the same time, and a warp drive that still involves acceleration still builds a horizon. The same goes for the biological exits: hibernation, torpor, frozen embryos, transmitted minds. All of them are proposals for making the traveller's clock irrelevant. Every one of them dodges the first wall and none of them touches the second or third. A sleeping crew still cannot receive a message sent from Earth after day 354. A frozen embryo still shares no present with the people who froze it. There is also a version of this that does not require any relativity at all, and I think it is the one that lands hardest, because it applies to missions we could actually launch. It is called the weight calculation, worked out by Andrew Kennedy and published in the Journal of the British Interplanetary Society in 2006. The observation is this: our maximum achievable spacecraft velocity has been growing at something like 1.5% a year. If that continues, then for any given destination there is always a later launch date whose ship overtakes the one you could send today, which means it is always rational to wait, and a civilization that reasons that way never launches at all. It simply keeps improving the engine and keeps postponing the departure forever on impeccable logic. The trap is not biological, it is not technological, it is not even, strictly speaking, about travel, and we now have everything we need to say what it actually is, because underneath all three walls there is one law, and it has been running the whole time, and it did not wait for anybody to build a ship. Everything I have shown you tonight comes from one sentence, and I want to say it now, because we have finally built enough underneath it for it to mean something. Of all the possible paths through space-time between two events, the one that accumulates the most time is the path with no acceleration at all. That is it. That is the law. It is called the principle of maximal proper time. It is a theorem rather than a hypothesis, and it is what every one of our walls has been an expression of. Look back at them with that sentence in hand. The first wall, the receipt written in someone else's currency, is just this law applied to a round trip. The traveller accelerates and the stay-at-home does not, so the traveller's path is shorter, so the traveller's clock has fewer seconds on it. That is the entire twin paradox, and the reason it stopped being a paradox is that only one of them bent their path. The second wall, the loss of a shared present, is this law applied to the question of what at the same time means. If different paths carry different amounts of time, then there is no universal timekeeping to hang a shared present on. The now that everybody assumed was out there was never a feature of the universe. It was a feature of everyone having taken nearly identical paths. The third wall, the horizon behind the accelerating ship, is this law applied without limit. Keep bending your path forever, and the deficit relative to everything you left grows without bound, and at some point the gap becomes causally unbridgeable, and that point is a surface, and it sits just under a light year behind you. 4 walls, 1 law, and the law has nothing to do with spaceships. I want to sit with the strangeness of the law itself for a minute, because it is genuinely upside down. In ordinary geometry, the way to travel the greatest distance is to move as much as possible. If you want a big number on the odometer, you drive. In space-time, the way to accumulate the most time is to move as little as possible. Ideally, not at all. The person who has lived the most, in the strict physical sense of having the largest number of seconds on their own clock between 2 given moments, is the person who did nothing, who sat still, who never accelerated, never travelled, never went anywhere. Let me put 2 lives side by side, because I think the theorem lands better as a picture than as a statement. Take 2 people born on the same day. One of them does everything. They go into orbit, ride transfer trajectories out to the planets, take the long burn out toward another star and the long burn home again. Every journey, every acceleration, every turn. The other one stays exactly where they are, never flies, never orbits, sits in one chair in one room for the whole of their life. Both of them experience 1 second per second, all the way through. Neither of them notices anything. Neither of them feels time doing anything unusual, because time does not do anything unusual to anybody, ever. And at the end of every possible path between the day they were born and the day they die, the one containing the most of their own life, the most seconds, the most heartbeats, the largest number on the odometer, belongs to the one who never moved. That is the theorem, and it is not a poetic flourish. It is what the geometry says. The greatest possible amount of your own existence is obtained by staying exactly where you are. I am not offering that as advice. It is not a moral. It is a fact about the shape of the road, and the amounts involved for any human choice are so small as to be meaningless. Nobody has ever lost a measurable fraction of a life to going places. But it tells you something about the structure of the world that I find hard to shake. The universe is arranged so that motion costs you time, not metaphorically, not as a figure of speech about busy lives, literally in seconds, measurable with a cesium clock. There is a version of this that physicists find beautiful rather than unsettling, and it is worth mentioning because it shows how deep the principle runs. In general relativity, this same law is what gravity is. An object in free fall, a dropped apple, an orbiting satellite, a planet going round a star is not being pushed by anything. It is simply following the path through curved space-time that accumulates the most proper time available to it. Falling is not a force. Falling is a body taking the longest possible road. The apple that leaves the branch and the moon that circles the Earth are both doing the same thing, which is nothing at all, as efficiently as the geometry permits. Which means that the law behind all 4 of tonight's walls is not some obscure clause in a specialist theory. It is the same law that holds you in your chair, and you have been paying it. That is the part I most want you to take away from tonight, because it is easy to file all of this under things that would happen to hypothetical starship crews in a century nobody here will see. You have never once been at rest. Right now, sitting wherever you are sitting, you are moving. The Earth turns beneath you at up to 465 meters per second at the equator. The Earth carries you around the Sun at 29.78 kilometers per second. The Sun carries you around the galaxy at about 230 kilometers per second, once every 230 million years or so. The galaxy is falling toward the great attractor at 600 kilometers per second. There is no version of you that has ever been motionless, and there is no frame you could move to in order to become motionless, because motionless is not a thing that exists, which means the meter has been running your whole life. Compared to a hypothetical observer who was somehow at rest, you have lost microseconds. Compared to somebody at the top of a tall building, you are losing nanoseconds every year, because you are lower in the Earth's gravitational field. The NIST people measured that with a 33-centimeter staircase step. Your head is aging faster than your feet right now, and the total across a lifetime is about 90 billionths of a second, and it is real. And the second wall has been running too. Your definition of what is happening at the centre of our galaxy has been sweeping through 5 years of that place's history, back and forth, twice a year, since the day you were born, purely because the Earth reverses its orbital direction every 6 months. Your definition of the present in the Andromeda Galaxy has been sweeping through 5 centuries. Nobody told you. Nobody could have told you, because there is nothing to feel and nothing to measure. You have been inside this mechanism your entire life. Interstellar space does not do this to a traveller. Interstellar space is simply the first place large enough for it to become visible. It is also the answer to a question that may have been forming while we went through the walls, which is whether any of this could be different. Whether a slightly different universe, one with a different speed limit or no speed limit, or a different sign in the geometry, might have allowed travel without exile. The answer appears to be no, and the reason is that the same minus sign doing all the damage is the one holding the universe together. That single sign in front of the space term is what makes cause and effect work. It is what stops effects preceding their causes, what gives every event a definite past and a definite future, what makes the word before mean something. Remove it, and you do not get a friendlier universe for travellers. You get a universe in which nothing can reliably follow from anything, in which no signal has a direction, and in which nothing like a person could form in the first place. So the 4 walls are not an unfortunate feature of an otherwise well-designed cosmos. They are what causality costs. The universe permits ordered events, and the price of ordered events is that shared time has a range. And I think that is why this particular corner of physics is so easy to misunderstand, and why the phrase time slows down survives despite being wrong. We keep looking for something that breaks. We keep expecting an effect, a malfunction, a distortion, a clock that stumbles, a body that ages strangely. There is nothing to find. Every clock in this story has been perfect from beginning to end. Every traveller experiences a completely ordinary life at a completely ordinary rate. Every physical law holds exactly as written aboard the ship, in the same form, with the same constants, including the speed of a light itself, which every observer measures as identical no matter what they are doing. Nothing is damaged, nothing is distorted, nothing is slowed. What breaks is not any object. What breaks is the correspondence between two intact realities, the exchange rate between one perfectly functioning life and another. Both halves are undamaged, both halves are unreachable from each other, and the space between them, which everybody had assumed was empty, turns out to have been holding something up. Which brings us finally to the question we started with, and I can now answer it properly. At the start of tonight, I promised you that by the end you would know exactly how time traps you in interstellar space, and I said it was not the thing you were expecting. So here it is, and I will give it to you in 3 pieces because it arrives in 3 pieces. The first piece is that time does not trap you by running slow. It traps you by ceasing to be shared. Nothing slows down. That was true in part 2, and it has been true in every part since. Every clock in this story has been perfect. The traveller's heart beats at the ordinary rate, the coffee cools at the ordinary rate, the cesium ticks at exactly 1 second per second all the way to Andromeda and back, and the people at home have exactly the same experience, uninterrupted, ordinary, unremarkable. 2 intact lives, both fine. What is missing between them is a shared present. At interstellar separations, there is no fact of the matter about what is happening somewhere else right now. The answer depends on how fast the person asking happens to be walking, and every answer is equally correct, and there is nobody in the universe who could adjudicate between them. 2 people passing on a pavement disagree about Andromeda by 4¼ days. The Earth's own orbit swings your definition of the present at the galactic centre through 5 years, twice a year, for your entire life, and you have never felt a thing. That is the trap, not a slow clock. A missing now. The second piece is that the only tool that shortens the trip is the same tool that seals the door. Sustained acceleration is what compresses a galactic crossing into a human career. 12 years to cross the Milky Way, 28 to another galaxy, at one comfortable gravity, in a ship where you could put a cup down and it would stay put. And sustained acceleration is what builds a horizon 0.9687 light-years behind you and closes it after 354 days. 354 days, under a year, half a light-year from home, still inside the shell of comets that orbits our own sun, still close enough that a hypothetical observer on Earth would say the ship had barely left. And from that moment on, everything anyone at home ever says is already lost. They will keep talking. They will have no way to know. There is no signal, no discontinuity, nothing to distinguish a traveller behind a horizon from a traveller who has simply gone far away. And you cannot buy your way out by pushing harder, because pushing harder brings the wall closer. There is no setting on the dial. The escape and the imprisonment are the same instrument, and you cannot have one without the other. The third piece is the one I would most like you to keep, because it is the piece that turns a physics fact into a trap. It is not reversible, and it was never optional. It is not reversible because in this geometry the do-nothing path is the longest one, which means every journey is a subtraction from your own supply of experienced time, and coming back does not add any of it back. It subtracts again. There is no maneuver that runs the meter the other way. The universe does not contain that operation. And it was never optional because you have been paying it since the day you were born. You have never once been at rest. The planet turns, the planet orbits, the sun circles the galaxy falls towards something in Centaurus, and against a hypothetical motionless observer, you have been losing microseconds continuously for your entire life, and your definition of now at the far side of the galaxy has never held still for a single day of it. So the trap was not built by the distance, and it is not sprung by the engine. It was already closed. It closed before anyone left, and it will still be closed for anyone who never goes. Which means the first traveller who ever leaves for another star is not going to lose a shared present at the moment of departure. They're going to find out that nobody ever had one. There is a philosophical shadow cast by all of this, and I want to name it before we close, clearly labelled as speculation, because it is where a lot of people end up when they follow the second wall to its conclusion, and it deserves to be handled honestly rather than dramatically. The argument runs like this. If your plane of simultaneity can be tilted to include events in another galaxy's future, and it can by walking, and if every observer's plane is exactly as valid as every other, then those future events must in some sense already be there to be included. Push that and you arrive at what philosophers call the block universe, a four-dimensional structure in which past, present and future all exist together, and the passage of time is a feature of how a mind moves through the block, rather than a feature of the block itself. Hermann Weyl put it about as well as anyone has. The objective world simply is, it does not happen. Einstein wrote something similar in 1955 in a letter to the family of his friend Michel Besso, 3 weeks before his own death, that the distinction between past, present and future is only a stubbornly persistent illusion. I am not going to tell you that is settled, because it is not. The physics establishes something narrower and rock-solid, which is that no observer-independent present exists. Whether that means the future is already real is a further step, and there are serious philosophers who decline to take it, and no experiment distinguishes the positions. There is also a clean practical answer to the version of this that worries people most, which is that you cannot act on your tilted present. Every event on that slice is causally sealed off from you. You cannot see it, reach it, influence it, or learn anything from it early. The disagreement is real, and it is inert. So the honest position is this: relativity has definitely removed the universal now, and it has definitely not told us what to put in its place. That question is still open, and it has been open since 1905, and some of the best minds of the last century have simply lived with it. I want to be careful too, not to leave you with the wrong feeling about the traveller, because there is a version of this that sounds like a horror story, and it is not quite one. Nothing bad happens to them. That is the thing worth holding. There is no moment of damage. They are not stretched or frozen or slowed or diminished in any way. They live an entire ordinary life at an entirely ordinary pace, in a ship where the coffee sits flat and the floor is where floors go, and they see things no one else will ever see, and every physical law they can test behaves exactly as it did at home. If you could visit them, you would find nothing wrong, and nothing bad happens to the people they left either. Their lives run on in full at the ordinary rate. They are not waiting in some suspended state. They have their whole existence with all of its seconds intact. Both halves are perfect. That is the entire cruelty of it. The trap does not damage anything. It just removes the relationship between two undamaged things and leaves both of them whole and unreachable and correct. I want to end where we began, because it is a smaller and quieter picture, and I think it holds the whole thing. In November, at 16 minutes past 2 in the morning, a machine built by people who are now mostly dead will cross a line nobody drew, at 16 billion and 94 million miles from home. It will not notice. It carries 2 working instruments and a fading supply of plutonium, and a gold record nobody's going to play. It has been flying for 49 years, and in all that time, at the fastest sustained departure speed our species has ever achieved, it has fallen behind our clocks by 2.5 seconds. 2.5 seconds at one end of this, 87,000 years of exchange rate at the other, and in between, nothing anybody can build. But Voyager has already passed the line that matters, and it passed it long ago. Nobody can ask it a question and get an answer in the same day. Nobody can say what it is doing right now, because there is no such thing as what it is doing right now. Only what a particular observer, moving at a particular speed, would be willing to call now, and the next observer would disagree, and both of them would be right. We tend to think of a shared present as one of the basic furnishings of reality. It feels like a flaw. 2 people are alive at the same time. The sun is up somewhere while it is down here. The world is happening all at once, everywhere, and we are all in it together. It is not a flaw. It is a courtesy. One that a very weak gravitational field and a very small set of speeds have been extending to us, quietly, for the whole of our history, because everything we have ever loved has been close and slow. And somewhere out past the Oort cloud, at about the distance where a ship under one gravity would find its door closing, the courtesy runs out. That is how time traps you in interstellar space, not by slowing down, by no longer being something 2 people can be in at the same time. Sleep well, and if it helps at all, you are, at this exact moment, taking the longest possible route through space-time available to you.